Hello, and welcome to a presentation on volcanoes in Washington, their threats, their hazards, and what you can do to be more prepared for this hazard in Washington. My name is Brian Terbush. I'm the Earthquake and Volcano Program Coordinator for Washington State's Emergency Management Division. So I focus on understanding these hazards and what you can do to be more prepared for them. I'm working with the other organizations like the USGS Cascades Volcano Observatory, running our shakeout drill every year, a great opportunity to practice your earthquake hazards, and what you would do to protect yourself, and just here to share a little bit of information about why we have volcanoes, some of the science, as well as the threats that you might face in different parts of Washington. But then again, most importantly, what you can do, because these are huge hazards, and it's easy to look at a volcano, a mountain that can explode, and just look at how quickly the landscape changed in 1980 when Mount St. Helens erupted and think, there's nothing I can do about that. But I assure you there is. You have opportunities, you have things you can do. So I hope that this provides a little bit more information about that for you. So why do we have volcanoes? Why do we have all these hazards? Because Washington is an exciting place to live. So we have a map here showing our Cascadia subduction zone, where the Juan de Fuca plate is subducting beneath the North American plate. So our North American plate is a less dense type of rock. So it floats on top of the mantle, and the Juan de Fuca plate is a more dense oceanic crust. So it dives underneath the crust. Now, because of that, where these plates come together, they build up a lot of friction. When they overcome that force of friction as they're pushing together, they can slip, and that can create our subduction zone earthquakes. Just the pressure between these two plates is also why we have a whole bunch of faults throughout our state, and why we get these deep earthquakes like the Nisqually earthquake. But I'm going to focus on the volcanoes and why we have those. So deep in the subducting plate here, you can see that in this area, there are some minerals within the crust that contain water. And as that water, as it dives deeper into the mantle, the temperature increases. We're looking at about 30, 50 meters or miles deep at this point. So when it gets down there, it gets warmer, and that causes some of that water to leave the mineral structures, which also makes them brittle. They can snap, which is why we get these deep earthquakes. But as that water leaves, it moves into the mantle here. And the mantle, because of that, it is able to actually melt. It's typically more of a plasticky, it's not a liquid mantle, but it melts, it becomes liquid. And as it melts, it becomes buoyant, and it forces its way up through the crust. So that's why on this area, very parallel to the subduction zone, you can see subduction zones here. We have this pretty parallel line of volcanoes from Canada all the way down to, say, Mount Shasta, Lassen Peak in California. And that's all related to this subduction zone here, all our volcanoes in Washington and Oregon. It's because when that part of the mantle that melts moves up through the crust, as soon as it breaks the surface, it can start erupting, and that's where we get these volcanoes. So the very basics we want to say about these volcanoes. We have 5 active volcanoes in Washington, and we'll go into what those are in a little while. And what we mean by active is they have erupted in the past 10,000 years, all of them have, and they're all in a state of just add magma. It's really hard to detect what exactly is going on deep within the crust, and we can't predict when that magma is going to enter those volcanoes, but as soon as it does, that puts them in a state of unrest where they could lead towards an eruption, and they could start erupting. Something like Mount St. Helens in 1980, or more like 2004 St. Helens. Very different eruptions, but definitely possibilities. So because of that, just add magma, I want you to understand that all of our volcanoes are well monitored. They won't erupt without warning. The one thing that's the alternative to that is landslides, or landslides that turn into lahars or volcanic mud flows, we'll talk about in a little while. They are possible, but that's extremely low probability. That's the least likely thing to happen, but we prepare for it just in case. So eruptions can't be predicted. The details of what happens when a volcano erupts, they can only be forecast. And USGS Cascades Volcano Observatory has gotten very good at that, looking at volcanoes all over the world, in addition to our own. So they get better at forecasting, but again, it's only a forecast, kind of like a weather forecast. It's not always right, but you can get a good idea of what might happen. So because of that, there's a high degree of uncertainty associated with eruptions. Just some of these things, thinking about when they'll erupt, just maybe tell like a 2-week window, it's very likely that blank will happen, but what they will erupt, what kind of magma is going to come out, what kind of lava, whether it will explode, whether it will have lava flows. These things are very difficult to predict, in addition to how long the eruption is going to last, whether it's going to be just one and done, or whether it's going to be a series of days, weeks, months, even years volcanoes can continue erupting for. So hazard maps, this is a tool that exists so that you know what could happen when the volcano erupts, and you understand which areas are most likely to be impacted by which hazards. This is a key tool for getting prepared for an eruption in your area. And then finally, understand those hazards in your area and know how to get alerted. I'm going to go into more detail about all of these things, but that's the basics. That's the outline. That's what you're going to need to know. So let's look at our volcanoes here. So in the US, we have 5 volcano observatories run by the United States Geological Survey that are in charge of watching 161 volcanoes. So they've looked at all these different volcanoes and kind of gauged what their risk is, what the threat is from each of these volcanoes. And that's all based on how often they erupt, how many people might be impacted when they erupt. And mainly those two are the really big ones, but the frequency of eruptions as part of that as well. And then it's kind of combined with what they erupt and how many people are potentially impacted by that. So for example, something that has a huge explosion like St. Helens in 1980, for example, that can cover a large area. So it puts a lot of people at risk, which puts it very high on the list. Whereas Mount Rainier, a lot less explosive, but its Lahars put a lot of people at risk. These mud flows that can go down the river valleys where 90,000 or so people actually live. That puts a lot of people at risk, so that's extremely high risk. So they looked at all these volcanoes and determined that there's 18 very high threat, again, based on how many people are at risk from their hazards. 39 are high, 49 are moderate, 34 low. Now you can see if you look at this list, Washington has 7 active volcanoes here that are monitored. We're only going to focus on the top 5 here, the high and very high threat, because our other 2 are these things called volcanic fields that are really, really, really unlikely to erupt again, and they're in pretty barren areas where not many people live. So they don't even consider those very likely to erupt. The areas are still monitored. If something was going on there, we would get warning just based on the seismic signals and things like that. But those are considered very low threat compared to our other volcanoes. So what are our volcanoes? St. Helens or Luetla. Number 2, it just erupts so frequently that it outranks Mount Rainier, even though Rainier puts a lot more people in danger. Mount Rainier is listed as number 3 in the US. Again, those Lahars, and this is Rainier Tahoma, more different name for it. Moving up to number 14, Mount Baker or Kulshan, and then at 15, right behind it, Glacier Peak or Dacobed. And then finally, we have one that's only in the high threat area. It doesn't put as many people at risk. It does not erupt nearly as often as the others, Mount Adams or Pato. Number 1 is Kilauea in the US, our volcano in Hawaii that is just constantly erupting. People live right on the slopes. And you saw in 2018, a whole bunch of homes destroyed by that lava flow. So that, just based on number of people at risk and how often it's erupting, is considered a higher threat. But because of this, again, all of our volcanoes are monitored as well as possible. So what does that mean? Yeah, let's look at our volcanoes a little bit and see how often they've erupted. So red line right here, 200 years ago, we're looking at the last 4,000 years of eruptions. You can see all of our volcanoes have had eruptions, some more frequent than others. And the one thing that they're going to need to change on here, I spoke with USGS recently, and they determined this was not an eruption actually at Mount Rainier. People thought in the late 1800s that there was an eruption going on, but there's no geologic evidence that that was the case. It was more from Explorer's Journal that came out. So no evidence of that. But looking at this clearly, you can see in the last 4,000 years, Mount St. Helens has erupted the most. But Rainier is not too far behind. I mean, Glacier Peak's had a number of eruptions as well, and Mount Baker has had a period of activity, even though it didn't have an eruption. So looking at all these, the other thing I want to bring to mind here is each of these little volcanoes on the map here, that represents a period of eruption or a period of volcanic activity. It doesn't necessarily mean just one explosion, one event like that. What each of these represents is a period of time, and that could be days, weeks, months, years. It's really hard to tell because we weren't there, but when you look at the deposits, you can date those and determine when these erupted, in addition to what they erupted. So again, if I had to make a bet on which one is going to erupt next, probably St. Helens. So one thing we want to get across about this as well, I've been mentioning that days, months, years of eruptions. Volcanic eruptions are very unique when it comes to natural hazards. Think about the warning time we get for floods, for hurricanes. You can get days of warning for that. You get those cones of uncertainty. You're not sure exactly that it's going to occur, but you get those few days of warning where you can start to prepare, and then they're going to last for days. Earthquakes, we can't predict those when they're going to happen, but we can get a couple seconds of warning thanks to Shake Alert Earthquake Early Warning System. But once those occur, you're going to get aftershocks for a while afterwards, but it's just up to 5 minutes of shaking in the very biggest ones, and then they're over besides the aftershocks, but no prediction at all. In wildfire, you can predict conditions, but you're not going to get that until the start, but then they can last weeks to months, so a little different. With volcanic eruptions, you can have days, weeks, months, years of warning before they occur. It's not really warning as much as it is just a period of volcanic unrest, where you know there's some magma in that volcanic edifice, but you're just not sure what it's going to do or when it's going to do it. Now, once that eruption actually begins, once magma starts leaving the surface, becoming lava, that can last days, weeks, months, years, decades. So they're pretty unique here. And when we look at this hazard and we have to start planning for it, preparing for what might happen, it gets really challenging. So an example of that is as emergency managers, as community officials, people have to start making decisions before we know exactly what the volcano is going to do. So this graph here, if you think about the intensity of those monitoring parameters, think about what's happening at the volcano. Are there increased earthquakes that are rising up in the volcanic edifice? Is it inflating? Is there increased heat flow? They're watching all of these things really closely. But again, those are just the first signs of volcanic unrest. So as those increase over time, you're going to reach this point where people have to start making decisions. The volcano looks like it's going to erupt, even though we don't know for sure that it is or not. So at that point, what do you do? Do you evacuate communities around it? Do you lower the water in dams to potentially catch Lahars? What are the decisions that can be made? Because all of those decisions are going to affect the community, the people there, if they have to evacuate. If you have to close recreation areas, that's going to affect the economy, especially depending on the season. So all these different things have to be taken into consideration. And then how do you do that equitably for everyone? So when you make these decisions, you don't know if it's just going to erupt really quickly. That would almost be the ideal case, especially if it's a small eruption, because you planned, you made decisions, and then it erupted. That's good in a way. You plan and make decisions, and then it doesn't erupt. It stops showing any signs of eruption. That's always a possibility too. I mean, we look at this eruption. This is pretty much how Mount St. Helens behaved back in 2004. It started showing signs of activity, these drumbeat earthquakes, and then pretty much 2 days after it started doing that, it started pumping out this lava dome. So it's a lot of work for the observatory, for the emergency managers who had seen 1980 and knew what was going to happen, or knew what might happen from this mountain because they'd seen it erupt before, and then it started doing something really quickly. You can look at that 1980 as more like this. We had 2 to 3 months of activity where it had some small explosions, but it wasn't really doing anything big. And then it really had this big eruption about 2 months after it first had those signs. But the parks were closed. A lot of people were asked to leave. In Washington, we can't force people to leave. We can't make people evacuate. It's a home rule state. So that's part of why we want you to understand what these hazards are so that you can make an informed decision whether to evacuate or not. That's important. But then there's these other possibilities. The volcano can just go back to sleep. It might not erupt. And then there's these cases where, like Mount Baker in 1975, it spent about 6 months showing signs of activity, and then it didn't do anything. There was no 1975, 1976 eruption of Mount Baker. But they lowered the water in Baker Lake Dam. They closed the national forest around there. It impacted the community for about 6 months, and there was a whole bunch of speculation, a whole bunch of media, and then nothing, and that impacts the community. So this is really important that people understand these possibilities before making these decisions. So we've talked a lot about volcano monitoring. How do we know when a volcano will wake up? Volcanoes are kind of similar to us in the morning. It takes them different amounts of times to wake up. So that's definitely a possibility. So some ways that we monitor, talked about seismic a lot, earthquakes, tremors. There's a bunch of different kinds, about 4 different kinds of earthquakes you might see at a volcano. Some of them indicate magma movement. Some of them are actually movement on faults, because we're in these kind of unstable areas where there are faults. Like there's a Mount St. Helens fault. There's one that cuts through lower parts of Mount Rainier. We have a lot of faults around our volcanoes just because it's a very seismically active state. So the thing is, again, as that magma moves up through the crust, it's breaking new rock. It's breaking through, and it needs to break that rock, and that breaking rock and that moving fluid, it creates signals, and those signals can be detected by a seismometer. So that's one of the big reasons that we have seismometers all over the volcanoes. The more the better. The more seismometers you have, the deeper the earthquakes you can detect, the smaller the earthquakes you can detect. So that just gives you a lot better resolution, gives the scientists a better picture of what's happening there. You can also look at deformation. So GPS, like what we use in our car to navigate, is also really good for telling if a volcano is moving. If magma moves into a volcano, it might kind of inflate like a balloon. So you might get 2 stations on either side of the volcano moving further apart from each other, or it might deflate where they move closer to each other. And it can pick up these really, really tiny signals that might indicate magma coming in. So our scientists at the observatories watch for these very closely. There's also tilt meters, which can also detect that deformation if they're very sensitive and can detect if, say, if the volcano is tilting up a little bit. So those are placed pretty far away from the mountain, but close enough that you can actually detect magma. And so they're a sign of shaking. Some more monitoring methods can detect gas. So a lot of our volcanoes, they're active volcanoes. You go near the top, you might smell hydrogen sulfide or rotten egg smell. That's a good gas to monitor. And so the scientists go up there at Mount Baker, for example, and just every once in a while, just kind of take readings of what kind of gases are present. Same with taking stream temperature and chemistry, because those streams, a lot of them come right out of springs on the side of the mountain. So the things with monitoring those over a long period of time, it's like going to the doctor for an extended period of time. You get this picture of what is normal for you. So you can tell which gases are normal at Mount Baker and what normal stream temperatures and chemistries are, so that you know if magma comes in, it might interact with the water. You get these gases moving up through. It might change the chemicals that are in there. It might heat up the water. It might change the gases that come out. So watching these over time, you can get a sense of when something changes. Again, kind of like those doctor visits. Your blood pressure has been pretty steady for a while. When it changes, it might be a sign that something's happening. So these are just more methods. And then finally, visual. Sometimes you can just look at a volcano and tell that it's different, which can happen sometimes. Just how quickly the dome on the north flank of Mount St. Helens was bulging in 1980. It was pretty clear that something was happening there. Now, it took some instruments to actually measure how much it was moving, but it was clearly changing. So sometimes even people that live near the volcano can just call in and report something's happening here. Okay, so again, one of those points of uncertainty is what is going to erupt? What is a volcano going to do when it erupts? And think of this picture here as kind of like the Swiss Army knife of materials that might erupt from a volcano, things that might happen. And there's a wide variety, and this is why it's so difficult to predict what might happen. What it's going to do depends on your magma type, how much gas is in it, where the vent is on the volcano, whether it's on the north side or whether it's right at the top. How much snow is on the volcano can impact what is going to happen when it erupts. Chemical weathering, sometimes just getting a lot of hot acidic fluids going through a volcano can cause it to become a little more unstable, more likely to collapse and have these landslides or debris avalanches. Just how fast the magma is moving through the volcano. And more. There's just all these variables that make it difficult to predict these. So here's just an example of some of these hazards, and I'm going to look at a lot of these in more detail over the next couple slides. But each one of these pose their own unique challenges. So when that volcano is in that period of unrest, the scientists at the observatory are going to be looking at They're going to be looking at the gas. They're going to be looking at the seismic signals and how fast the magma is rising. And they're going to be looking at histories of what other volcanoes around the world have done in times like this. For reference, you hear news stories about volcanoes and it seems like it's just, wow, there's a big one. At any given time, there are between 40 and 50, 55 sometimes volcanoes erupting on Earth's surface. So it's not as abnormal as you might think. And there's some where it's just our volcano is erupting today and people are very used to it. That's just the way it is. Now, ours aren't like that. So anytime one of them starts to show a sign of activity, we're going to get a lot of attention really quickly. So even think about that as a potential impact. Just the number of people in news and media that is going to flock to the area just to get a glimpse of this and potentially be there for an eruption. Mount St. Helens kind of turned our volcanoes into like celebrities coming to town. They're rare events on the US mainland, and it's just interesting to people. So all of these things could happen, and I'll talk about some of them in more detail. But again, this is the Swiss Army knife. All of these things could happen. Some of them might happen concurrently at the same time, but it's very unlikely that all of these will happen at the exact same time. That would be pretty bad. So one way we know what a volcano might do is looking at its history. What will a volcano erupt? It's kind of an axiom in geology: study the past to understand the present and what the possibilities are for the future. So they look at deposits from these old volcanoes, from old eruptions, to understand what future eruptions might do. Because typically a volcano is going to keep doing the same thing over and over again. It has this typical style of eruption based on the type of magma that is in the volcano itself. Now, for example, here's a deposit. This is Mount Rainier's Osceola mudflow from when Mount Rainier did something similar to Mount St. Helens in 1980. It had a sector collapse where a large portion at the top of the mountain actually collapsed as part of the eruption, and it turned into this massive mud flow that moved downstream. So how big is it? This is just the deposit. This isn't even what was flowing. But this 31 miles downstream, and this is on the White River, this deposit is 26 feet thick. So if you look at those boulders in there, this is just an example of what a lahar is, a volcanic mud flow. And again, this is just what was deposited and left behind. So this was a big enough lahar that it actually reached the sound. So these can travel very far downstream. But when we look at those and put them all together, you can understand what the hazards are. And that's how actually these volcanic hazard maps are constructed. So for example, we have one here from Mount Rainier. We have these for all of our volcanoes in Washington. So things that this does show: near volcanic hazards and downstream hazards. The one thing it does not show is volcanic ash. So anytime you get an explosive eruption, ash is going to move downwind. We don't show that on the hazard maps because downwind varies depending on the day. In Washington, it's usually to the east generally, but there are a few days per year where it's going to blow to the west and potentially impact people there. Near volcano hazards is covered by this pink area on USGS's hazard maps. What these are your disaster movie hazards. I like to think about them: really fast moving, quickly evolving, unpredictable. Your pyroclastic flows, your volcanic bombs, tephra, really, really heavy ashfall, lava flows themselves, and big landslides. Downstream hazards, we get these reds, these oranges, these yellow colors. These indicate areas where lahars and further flooding can occur as a result of this. All of our volcanoes are typically covered in a lot of snow and ice. And when an eruption occurs, whether it's lava or a pyroclastic flow moving across that snow, it can melt. And when it melts, it can move downstream really fast. So all of these streams represent areas where those lahars have deposited in the past. Again, just volcanic mud flow, a mix of ash, debris, dirt, whatever it picks up as it moves down, and all the debris it picks up as well. So go into those in a little more details. Let's look at ash first. Volcanic ash is not the same as the ash in the air during forest fires. This is little tiny pieces of lava fractured by the explosion. It's a lot closer to like glass. It is silica, so it's made of the same thing as sand, but just really tiny pictures. Small amounts flying around in the air, a few millimeters deposit or less. It's a nuisance. It's not fun to breathe in. It's low air quality. But large amounts can actually get to the point where they're dangerous, as much to your health, but it's really hard to drive in. Remember the eruption in Iceland of Eyjafjallajökull? That's just fun to say, so I have to say it. That where it actually covered all of Europe, and they shut down air traffic for, I believe, a couple of weeks during that eruption, because they were concerned about the impact ash would have on volcano engines. 4 inches of ash, if it becomes wet, it's heavy enough to collapse roofs. So some examples from 1980, that's our biggest recent memory of volcanic ash, but it's really, really easily remobilized in the air. So anytime you drive around, it's going to get kicked up again, and it can coat crops and everything. Our biggest hazard from ash comes from Mount St. Helens and Glacier Peak. These volcanoes have both produced a huge amount of ash in the past. We remember 1980 Mount St. Helens. Ash traveled all the way into Montana. At least a centimeter of it was deposited in those areas in this thin band. Glacier Peak, back 14,000 years ago, had an eruption that was larger than that. And St. Helens has had some larger ones in the past too. So just the size of those explosions, they can deposit a lot of ash. Now, Rainier, for example, its largest explosion they found deposits from is actually only about 1/10 the size of the 1980 eruption. So still pretty decent size eruption. Could cause some trouble, especially in areas nearby with the ash. But the bigger problem from that is going to be these Lahars, volcanic mud flows. That's a lot more of a danger. So near volcano hazards, that pink area around the mountain, we want to look at what these are. So tephra, really heavy ashfall, just any exploded material that's coming out of the volcano, and ballistics, which we call anything much larger than ash, pieces of rock, any of that that's flying out of the volcano when it erupts. This is really dangerous stuff, and you can't predict which direction it's going in. Lava flows, now ours are a lot different than the ones we have in Hawaii here. We have a lot more viscous magma. Typically it's called andesite when it comes out, the type of rock, which is typical of the Andes. That's where the name comes from, that whole chain that goes all the way down through Western South America. Very similar rocks here to there. Ones like Mount St. Helens have a lava more type of dacite, which is a lot more explosive. It's more viscous. So potentially a little more, it's the silica content that makes it viscous. So more quartz in that magma, more crystals of that variety actually makes it more viscous, more explosive potentially, unless it just pumps out as a dome like it could. And that depends on the gas content. Now, one of the big hazards with our lava flows is as they're moving down the slope, they can break up into rock falls. They can also break up into pyroclastic flows, which are the next page. But when we talk about tephra, ballistics, bombs, these were even a problem in the last Hawaiian eruption, where it actually had some good explosive eruptions. And this was an article there. No, Kilauea was not giving away refrigerators, but a slight headline here to say fridge-sized blocks were flying out of the mountain as it erupted. So some of these ballistics can get really big, which is part of the reason it's really important to stay out of these areas if they're closed, because you can't tell exactly when this eruption is, when these explosions are going to happen. So it's safer to stay away. More pyroclastic density currents, as they're called, or pyroclastic flows, they're often known by. This is your disaster movie cloud of gas, rocks, and ash that comes moving down the mountain at high speeds, usually very hot. Think unsurvivable in this case. Debris flows, lahar initiations, these can happen just as landslides occur on the side of the mountain. And all of these things are possible at all Washington volcanoes, which is why they have that near volcano hazard zone around there. So if a volcano goes into a state of unrest, highly recommend staying out of this area, because these things can happen very quickly without any warning whatsoever, even if the volcano is not actively erupting. It doesn't look like it. Downstream, we have to look at lahars. So I've mentioned that word a few times. It comes from Indonesia. A lahar is a volcanic mud flow of mobilized, especially ash, but anything that it picks up along the way. So for example, in Indonesia, where this word came from, they have a lot of volcanoes that erupt explosively. The sides get covered in ash, and then when they have monsoon rains come through, it picks up that ash, it mobilizes it, and you get these mud flows coming down the mountain. Now, ours are more likely to occur when melting happens during a pyroclastic flow, for example, or from a lava flow. anything like that, just melts all this glacial ice and starts to pick it up as it goes. So as they move down the streams, they are a mix of water, ash, and debris, common hazard from our glacier-covered volcanoes, most likely to occur during an eruption, but can rarely happen without one, which is the main reason we have a Mount Rainier Lahar warning siren system installed specifically for that reason in case of a landslide generated Lahar. So looking at these again, they can travel miles downstream from the event. Again, looking at these yellow areas, and those all just represent places where they found Lahar deposits from previous eruptions. This is a hazard at all Washington volcanoes, and they are highly destructive. Just for reference here, this is from 1980, Mount St. Helens. You can see this boulder floating on the top with a nice little rock hammer about that big on top of it that was carried on top of this deposit. That particular one destroyed 27 bridges as it went down the Toutle River. And that was kind of an interesting Lahar because it started moving down the slopes. Well, there was that big landslide. And then it was actually a couple hours later when the chunks of glacier inside that landslide melted that caused the whole piece of the mountain to turn into a Lahar and move downstream. So that happened after the main phase of the eruption. Yeah, so they can travel pretty quickly, especially on steep slopes. But then when they reach these flat areas and river valleys, they can spread out. They're still highly destructive and dangerous in those cases. The most important thing to know about Lahars is know how you're going to get alerted and how you're going to evacuate to high ground when they occur, because that is the only way to guarantee you're going to be safe. They can easily wipe out the buildings. You may not return to a home, to cars and things that could be buried by this Lahar, but you can be safe if you get out of the way. That's the most important part. So for an example on that, Mount Rainier has a Lahar warning system, and this is mainly because about 90,000 people live in the river valleys on the Puyallup and the Nisqually River that are potentially in danger from this. And part of that is because they've noticed about 500 years ago, the electron mudflow, it's called, was an event where Mount Rainier had a Lahar that occurred without any volcanic eruption. There's just no evidence that there was a volcanic eruption. And there's an area on the southwest side of the mountain. Again, I mentioned this hydrothermal alteration where you get this hot gases move through the rock and they just slowly turn it into, I think the geological technical term is crap. It's just this kind of rock that is really easy to disintegrate. And just that being exposed to the force of gravity over a bunch of years, it can potentially just collapse without warning and doesn't need the stress of a volcanic eruption to do so. So there's a concern that that could happen. Where that spot is located on the mountain, it would only go down the rivers to the southwest, the Puyallup and potentially the Nisqually. But as a result of that, we know that these communities downstream need a warning system so that they get warning that a Lahar is occurring, can get out of the way. Again, this is the least likely thing to possibly happen. Most Lahars, at least 9 out of 10 of them, will occur during an eruption, probably more than that. But that is there, and it will be there during an eruption too, to warn these communities downstream. The city of Ording has about 9,000 people living there. When those sirens go off, they have about an hour to get everyone out before the community is buried by this mud flow. And Puyallup's just slightly further downstream with a lot more people in that river valley. So it's really important that these people get warning. It's really important that everyone in the Lahar path gets warning. So know how are you going to get those alerts. But currently, Rainier is the only one where they found evidence of these Lahars that don't have any volcanic material in them. So if we find that, or if that's found at other mountains, maybe they will install other warning systems. And maybe we'll do that in the future anyway. I think that would be excellent. So they have about 41 sirens in the valley. They can go off and warn people. Okay, so learning your volcanic hazards. Going to sum up these hazard maps really quick so that you can look at one next time and understand what it is. Know what to expect. In your area, think about understanding those impacts. If a Lahar moves through, it's going to change the landscape. It's going to change the floodplain afterwards. Areas are going to flood that didn't before because it's pretty much like if you put a bunch of sand in a bathtub, you need less water to fill it up afterwards. You've just put a whole bunch of sand in your river system. Next time the river floods, it's going to overflood areas that weren't flooded before. So understand how you'll be alerted, and then how do you protect yourself? If there's just ash falling, then typically it's recommended to shelter in place. So you don't have to go out in that nuisance ash. You don't have to damage your engine or anything like that. But if it's a lahar, you need to evacuate. And you got to make sure that that's clear. Even if there's ash falling, the lahar is the more immediate life safety hazard, and you need to evacuate from that. You can put a cloth over your mouth and you won't have to worry much about breathing it, or a well-fit N95 mask. You know, there's a lot of those around at this moment, so that could work. So let's look at these different hazards on the hazard map one more time so you can tell what they are. This pink area, and this is my sing-along guide. I like to help you read a hazard map. So near, looking at those pyroclastic flow, this pink. So we got near, looking at these areas that are yellow, that are red, areas where lahar could happen. So near lahar, and then where is volcanic ash? Wherever you are. So near lahar, wherever you are. It depends. You'll have to look at weather forecasts in order to determine where the ash is going to go. But I hope that helps you read a hazard map and you can remember that each time you read it. Okay. Another thing you can know about these, again, we have well-monitored volcanoes, and the USGS is actually in charge of putting out volcano alert levels. So all our volcanoes are currently at normal. What they're doing is different for each volcano, but again, like those doctor's visits, we're checking up on them, making sure that we know what's normal for them. Mount Rainier has a lot of earthquakes every year. That's normal. It's an active volcano. Mount Baker has a gas plume that smells like rotten eggs. That's normal for it. If these things start to change, it's possible that the volcano will move up, into an advisory level. Now, this means that the volcano could be escalating towards eruption. It doesn't necessarily mean it's going to erupt, but it means that the signs are there that says there's probably magma in this. We're going to be watching it really closely. So in that case, you're going to see a lot more monitoring go on there. Install all those additional seismometers so they can detect all the minute stuff, every little detail of what it's doing. It might move up into a watch from there. And sometimes you can skip advisory and it'll just go right to watch or warning. On our well-monitored volcanoes, you're going to get some signs, especially because they have not erupted in a long time. It needs to break new pathways. The magma needs to get to there so it can start erupting. So a watch means it's exhibiting heightened or escalating unrest with increased potential of eruption. This kind of means that magma is close to the surface, and that's that really dangerous time to be in that near hazard zone, because you only need to look back at 2019, the Whakaari or White Island eruption in New Zealand to see what can happen when magma is really close to the surface. If that touches the water table, you can get these hydrothermal explosions that are really unpredictable and they can be devastating. Very violent explosions, which unfortunately happened there at that time. So just saying, if that area is closed, it's for your safety. Echo that here. Volcano might also be in a watch if it's erupting, but it's not actually posing any hazards to people. For example, Kilauea is very frequently in a watch because it's just erupting in its summit caldera. It's not really impacting anyone, and you can go watch it, and it's a really fascinating sight. A volcano in a warning means that there's a hazardous eruption going on, so it puts people in danger, or it's underway, or it's suspected. It could be about to erupt. This is kind of like there's a lot of pressure on the bottle. So how can you get these? You can get these at the same time we do at the State Emergency Management by signing up for Volcano Notification Service. You'll get an email when one of these levels changes, and sometimes you'll get information statements, which are just saying, we noticed this. So it's just kind of a sign that they're watching very closely. And we don't get those too frequently in the Cascades. But for example, last year at the Sisters Volcanoes in Oregon, they sent out an information statement to say, we noticed that there was about an inch of uplift over this huge area over about 6 months. So they notice really detailed things. And if you ever want to know that they're being watched, you can check on those. So safety continued. Follow the guidance. When you get that information from the volcano monitoring agencies, it is really tempting to go and want to watch these eruptions happen. But again, you can't predict when they're going to happen. And also don't do it in a way that's going to be unsafe or that's going to make it really difficult for the people in the area to keep people safe, because that's a really important part. Knowing those hazards in your area is really important. If you live in a Lahar inundation zone, you want to know how to get out. If you work or if you go to school or your kids go to school in one of those areas, You want to know how they're going to get out and what that reunification plan is. But if you commute through one, if you travel through one, understand just what those impacts might be on your life. A volcanic eruption doesn't have to send a lahar right through you to impact you. There are indirect impacts of these eruptions, and so some of those are going to last for years to decades. Um, so that's always a possibility. These lahars can take out power stations. They're along rivers, so there's a lot of potential impacts. Just know how you can be alerted for those, and you can have to prepare the way you do for other events as well. The other thing I'd recommend, if you really want to learn about the volcanoes, go to them, go enjoy them, because there's really excellent visitor centers. You can learn about their history, you can learn about their cultural impacts. People have lived around these mountains, given them names and personalities for thousands of years. You can look at all these deposits to learn what they've done in the past. And just go, they're beautiful, just go enjoy them, because they are a fascinating part of our skyline, and they're also a temporary one. We might not see them erupt in our lifetime, but we might. So just go enjoy them while they're not erupting. So what will our next eruption be? Again, we can't predict. We don't know exactly what's going to happen. If I were betting, I would say St. Helens just erupts the most frequently, but it could be any of them. As soon as that magma starts to move in, it could be multiple at once. There's not really a way to control these things. So just take some time to understand your volcano, what hazards it represents, and what you can do about it. That's all I can recommend. Just go enjoy them while you can and learn about your hazards. Tell the other people in the area. So some details, if you want to get those alerts, you want to sign up for volcano notification service from the USGS and connect to your local alerts. That's a really critical one because your community might have an alerting system, your county might. They'll provide information about not just volcanic eruptions, but also flooding, severe weather in your area, maybe a fire or an area to avoid. It's just really important to be in the know about these. And then if you have any additional questions about volcanoes, about ours, about plans, things to do, please feel free to reach out to myself. And then we always post information about our volcanoes and other geologic hazards on our Twitter account. We have a special geologic one here at Washington AMD, WASH Shakeout, very focused on the earthquake shakeout drill, but please feel free to follow us if you want more information on geologic hazards, because we're always sharing info there. Besides that, thank you very much for your time and taking the opportunity to learn about your volcanoes, and everybody take care.